We'll see a small problem, a small numerical on the load test. Then we'll move to Swinburne's test. Okay, so that we'll reinforce the uh, concepts. Okay. So following are the load test readings on DC shunt motor. Find the output power and efficiency of the motor. So the readings are spring balances 10 kg and 30 kg. So let the given things we note down. Okay. Let 10 and 30 kg, I will take S1 as 30 and S2 as 10 kg. Then diameter of breakdown. Let me take it as DRE pulley is equals to 35 centimeters. Line current IL is 31 amperes. Voltage V is 200 volts. Okay. So these are the given things. Okay. Then the speed is, this is not mentioned, speed is 950 RPM. So N is 950 RPM. Okay. So we know what is the efficiency, or first I have to find out the output power. So what is P out for load test method? It is 2 pi N, okay, into S1 minus S2. Now here I will specifically take S1 minus S2 because I know S1 and S2. Into 9.81 into R divided by 60 into V into I. So on the RHS, we know N, we know S1, S2, we know V, we know IL, but we don't know R directly. But we have the diameter of the pulley. Okay. So from the diameter of the pulley, I can calculate the circumference of the pulley. Okay. So circumference of the pulley or brake drum is equals to pi d.
Excuse me, sir.
Yeah.
You have written efficiency equation.
Oh, sorry. Then this way won't come. Yeah. Thank you for reminding. Yeah. Now this is a P out. So circumference of pulley is pi into d pulley equals to pi into it is 35 centimeter. So 35 centimeter is what? 0.35 meters. I want radius in meters because the torque, whatever I have calculated here, okay, this torque PSH is in Newton meters. So therefore my radius should be in meters. If I take this in centimeters diameter, then my circumference will be in centimeters. Again, I have to convert it into meters only. Okay. So diameter of the pulley is 0.35 meters equals to how much we'll get?
1.09.
1.09 meters. Okay. And this is equals to 2 pi r. The circumference of the pulley or circumference of the circle is given by 2 pi r. So 2 pi r. Therefore, radius of pulley R is equals to 1.09 divided by 2 pi equals to
0.175.
0.175 meters. Okay, next. This I have to erase. Okay. Now I can substitute in the payout equation. Equals to 2 pi into n. N is 950 into 30 minus 10. They are in directly kg, so no issues. Into 9.81 into 0.175 divided by 60. Into 20 into 9.81 into 0.175, okay, divided by 60. No, something went wrong. How much you are getting?
3.41 kilowatt.
3.41 kilowatts. Okay. This is equals to P out 3.415 kilowatts. Okay. Then P in is equals to V into IL. Okay. So this is equals to 200 into 31. It is 6.2 kilowatts. Therefore, efficiency is equals to P out by P in. You can calculate separately or you can substitute in the same equation, no issues. this is 3.41 5 kilo divided by 6.2 kilo. So it is 55%. So percentage efficiency is 55.08%, is it?
Yes, sir.
Okay. Yeah. So this is what these values indicate is, observe here, nowhere we have calculated the losses. Actually, when we were looking into the theoretical aspect of the testing, when I had explained the testing, what for we are doing testing of the motors, there what I told was the testing we do only to know the losses and the efficiency. Through losses we calculate efficiency. Okay. I told through losses we calculate efficiency. But here you observe nowhere we have calculated the losses. Okay. This is the beauty of load test. Directly I can get efficiency at any load condition. And I don't know whether the load is full load or partial load. Only the values are given. So this IL is equal to 31 amperes. I don't know whether it is a full load line current. It may be partial load line current also. Okay. So at any point of load condition, without knowing losses, I can calculate efficiency directly. Hence, it is known as direct method. One reason why it is known as a direct testing method, because directly we are applying the load. The second reason why I can say is directly I will get the efficiency just by observing the output and input. Just by finding the output and finding the input, I can get efficiency directly. And I'm interested more in efficiency. Now you may ask a question that if losses are not known, then how to calculate the rise in temperature? Is it? See, losses are used for two conditions. Losses are used for two conditions. One, to know the efficiency once input is known or output is known. If I know the output, I will add that to output and I will find input, take the ratio, get efficiency. If I know the input, if losses are known, deduct from input, get the output, take the ratio. That is for one reason. Second reason, by knowing the value of losses at various load conditions, I can find out what is the temperature rise. But in load test, though, because I don't know losses, how do I find the temperature rise? Anybody? Yes? How do I get the temperature rise in the load test? Because I don't know the losses. What type of testing method is this? Direct testing or indirect testing?
Direct.
Direct.
Direct testing. So we are applying the load. It means motor is running and I am applying it on the load. Can't you measure temperature directly there? By using temperature sensors, okay, you connected to various parts of the motor. Can't I get the temperature directly? Because motor is running on the load. Can I do it or not?
Yes, sir.
Say yes or no. Can I do it or not? Can I directly measure the temperature when motor is running directly? This is what happens if you don't use your ability and if you try to get the things done through somebody else. You people will be unable to answer even the direct and simplest question. Array, I have temperature sensors connected in the motor. The motor is running. The motor is loaded. Can I get the temperature rise value directly or not?
We cannot say.
Yeah, we will get it. So only it is called direct method, right? So directly I am getting efficiency by observing output input. Directly I am getting temperature rise. Then why should I calculate the losses? Even if I want to know the losses, deduct in output from input. Directly I will get the total losses. If I want copper losses, I know I will be knowing the resistance of the winding. I know line current. Calculate copper losses. Yes. This is the reason why this method is known as direct method. Okay. So when do I use losses to find the temperature rise? I use losses to find the temperature rise in all the indirect methods of testing, where I am not directly connecting the load to the motor, but still I find certain methods of testing through which I can know the performance of the motor. In such cases, by observing the losses value, I can calculate the temperature rise value. But whereas in direct testing method, I can directly measure the temperature either using various temperature sensors or by using direct thermometer method. Okay, IR sensors. There are various ways. There are hundreds of ways to measure the temperature, and there are different methods to measure temperature at different parts of the uh, machine. In the last semester, we had arranged a tech talk from this WEG Industries India Private Limited. Your senior had given a talk on the sensors of temperature measurement, where he had listed some 6 to 7 types of sensors. Okay, I know you won't remember that, but I just reminded you. Okay, so that is why it is called direct testing method. So these values what I get, it is from direct observation of the load readings. Okay, so this is about direct testing method. In the next method, what we see is Swinburne's test or no load test. Okay, so the next testing method what we will be looking into is Swinburne's test. You should be cautious while using the spelling of this person. He is a person, it is a person's name. I don't know what has happened with this. Okay. I have to buy new digital pad. Okay. Swinburne's Swinburnes. Don't write SWINE. That will become Swinburne's test. Swine, you know what does it mean? And many of people they pronounce like that only Swinburne's test. No, it is a Swinburne's test. So Swinburne is a person who proposed this testing method. Okay, and this test is a no load test. If I was in college, I could have used somebody else's pad, but now it is very difficult, becoming difficult. Okay, so this is a no load test. Okay, this is also known as, because we are not loading the DC motor here. Okay. So because it is no load test, this forms indirect method of testing. Okay, indirect method of testing. Okay, so here, whatever the efficiency I will find out by finding out the losses first. So in almost all the testing methods, what we see hereafter on the shunt motor or on series motor, okay, we all in all the tests we calculate the losses first, then we will calculate the efficiency. And because this is a no load test, it has to be used only for shunt motor and compound motor. Okay, so this is very important. Okay, applicable only for shunt and compound motor. Why not for series motor? First, somebody. And not for series motor. Somebody tell the reason first. Why can't I use Swinburne's test for series motor?
Series motor must be started on some loads.
Yes, I can't operate series motor on no load, as it cannot be operated on no load. It cannot be operated on no load. So we should keep it in mind that Swinburne's test is applicable only to shunt and compound motor. Okay. What we are doing here, we are predetermining the efficiency. Why I say predetermine? Because exclusively I say, even in the OC/AC test of the transformers in previous semester, it was asked to predetermine the efficiency and regulation. Why predetermination? Because I am not actually operating the machine on the load. So it is a predetermination. Without applying load only, I will be predetermining it. Okay. So here we predetermine losses and efficiency. Losses and efficiency. Okay. So the circuit symbol or the circuit connection for this, it is very simple. Motor, the diagram, circuit diagrams, what I am drawing, these are the circuit diagrams that are there exactly like in the manual. It will be easy for you to remember and connect the concepts. So I am taking the circuit diagrams as they are given in the practical experiments manual. Okay, I'm trying to keep as much as the same circuits possible. RHA, sorry, it cannot be RA, it is RHA. Let it be RHF, field rheostat and armature rheostat. So this ammeter will measure the line current IL, or we take it as I naught because it is at no load. This ammeter will measure the shunt field current ISH. Okay. So here we are doing test in 2 stages. Swinburne test is done in 2 stages. Okay. Test is done in 2 stages. In stage 1, what we do is, in stage 1, we find out hot resistance. We find out hot resistance. Okay, so what do you mean by hot resistance and cold? If I am telling hot resistance means there should be some cold resistance. Okay, so what do you mean by hot resistance and cold resistance? Hot resistance is the value of resistance of the winding after the temperature rise of the winding above ambient temperature value. That is, suppose ambient temperature of the motor is say around 35 degrees centigrade. Room temperature is say suppose 35 degrees centigrade. If temperature rise of the motor has gone beyond ambient temperature by another 40 degrees centigrade, so the total temperature of the winding is now 75 degrees centigrade. So the resistance at this temperature of 75 degrees centigrade, or just a moment. Sir, good morning. Yes, no, fine, sir. Sir, can I call you back? I'm in the middle of the class. Yes, sir. Once after the class, I will call you back, sir. Yes, sir. So, when the temperature of the motor is above ambient temperature, that value of resistance of the winding is known as hot resistance. Why specifically in this test we think about hot resistance is, the motor is not running on the load. The motor is running on no load. So the temperature rise of the motor is very least, or we can say negligible. At no load, temperature rise will not occur because the line current drawn by the motor at no load condition is hardly 10% of the full load current, 5 to 10%. In transformer, it is 1 to 2%, but in motors, it is 5 to 10%. Sometimes it is more than 50% also. In induction motor draws more than 50% no load current when compared to line current. If the line current value is 10 amperes, the no load current drawn by the induction motor is around 6 to 6.5 or 7 amperes. You cannot say, seeing that the motor is at 70% load condition. So by observing the line current of the load, in case of transformers and generators, we indicate the load condition, load factor. But in motors, we can't do that because the motors will draw the line current or from the supply even when they are in no load condition, because they have to overcome the rotational losses. Rotational losses are the major losses, or mechanical losses are the major losses that has to be overcome. So the motor is running at no load in this test. I am not at all loading the motor. So if I find out the resistance of the motor, it will be as good as cold resistance only. But if I want exact copper losses to be calculated under load condition, now I have to transfer this cold resistance to hot resistance. Okay, I have to transfer this cold resistance to hot resistance value. For that, there is a factor of 1.2. Now what I will do to get the hot resistance of the motor, I will find out the resistance at the cold condition. What do you mean by cold condition of the motor? When the motor is not yet started and nothing is connected to the armature. You may remember in the generator experiments in the last semester, whenever you wanted to find RA, we used to ask you to remove the connections, then find out RA. Okay. So whenever we want to find out the resistance of the winding, no connections to the winding are to be done. Okay. So we have to take the isolated winding resistance. If that is taken at cold state, that is when the motor is not running, because when I remove all the connections of the motor, obviously motor will not run. So that is the cold state. Okay. So in the stage one, I will find hot resistance. So what we do here, we find uh, winding resistance in cold state. In cold state, that is uh, motor not operating. Okay. And transfer cold resistance value to hot resistance value. And the factor is 1.2. And the factor is 1.2. That is R hot is equals to 1.2 times R cold. This is 40° above ambient temperature. 40° centigrade above ambient temperature. Suppose ambient temperature is 20 degrees. Then R hot is at 60 degrees centigrade. If ambient temperature is at 30 degrees, then R hot is 70 degrees centigrade. So 1.2 is having some small derivation, which we will not worry about. Okay, directly we will consider one case. This is how we can do it. Is one method. Second method, practically how we will do in our lab. Okay, practically how we will do in our lab. Generally, if you don't want to transfer like this, because ambient temperatures may be different, and I don't know exactly the temperature is at 40 degree, right? This factor of 1.2 is there, considering 40° ambient, 40° rise in temperature above ambient value. But I don't know now whether the motor will go to 40° temperature rise after beyond ambient value. So then how I should I do practically? So what I do practically is in my lab, even you do the same thing in our lab when you conduct. Practically what we do is we run motor on no load for some extended time after testing. For some extended time after testing. Okay, say for another 5 minutes or so. Okay, but actually we should run beyond that. But because of time restrictions, we will do that. We run motor on no load for some extended time after testing. Then uh, armature resistance is measured. Then armature resistance is measured immediately after motor is stopped. Immediately after motor is stopped. This is actually how practically we should take the hot resistance. Okay. We should run beyond 5 minutes. Some around 15 to 20 minutes we should run the motor at no load. Then immediately have to stop the motor, remove the connections, take the resistance value of armature using either VI method or multimeter. We generally use multimeter in our lab. So multimeter also employs VI method only. It will apply some voltage of 3 volts to 4.5 volts depending upon the batteries, how many we have. Then it will measure the current, it will calculate V by I. So that is VI method of finding resistance, DC resistance. Since this is DC motor, we use DC resistance. In AC machines, last time you calculated 1.5 times the armature value. You remember? RA in alternators or synchronous generators, you took RA is equals to, you got some per phase value of resistance 3.5 ohms. To that you multiplied by 1.5 again. So that is for skin effect. In AC machines, we observe skin effect. There is no skin effect in DC machines because the reactance of the in DC is 0. So therefore, we don't multiply skin effect value here. So whatever the value we get using multimeter, we take it. So actual way how to take the hot resistance is this, that run the motor after the testing for 15 to 20 minutes, then observe the value of resistance. Okay. But generally, our instructors, what they will do immediately after the test is done, they ask you to take the resistance, which is as good as cold resistance only. Because Swinburne's test can be finished in less than a minute once the connection is done. You have to run the motor, adjust the speed, and take the readings. Readings is that to voltage, current, and current. That's it. Okay. So this is stage one. This is stage one where we find out hot resistance. In stage 2, we find out constant losses. In stage 2, we obtain constant losses. Okay. So Swinburne's test will give us constant losses. Why only constant losses? Because motor is on no load. Variable losses are copper losses. If I want to find copper losses, then I have to connect the load or I have to assume the load. But this test is mainly on a no load, therefore it will give us constant losses. Okay, and one thing we should what we can say understand here is DC machine can be operated as motor as well as generator. The same machine without change in any constructional features, I can use it as generator or a motor. If I provide field supply and the armature supply, the machine will operate as motor. If I provide field supply and the mechanical input, it will operate as generator. So the advantage of these testing methods is that I can find out the efficiency of the machine when operating as motor as well as when operating as generator. Getting my point? I can predetermine the efficiency of the machine when the machine is intended to operate as motor, what will be the efficiency, and when the machine is intended to operate as generator, what will be the efficiency. Both will not be the same. Both efficiencies will be different. Okay. So the advantage of these indirect testing methods is that I can get the efficiency of the machine both operating as motor as well as generator, but that is not possible in my load test. In load test, whatever the breakdown test or the load test, we have seen, it is exclusively for motor. Okay, that has to be exclusively used for motor. Okay, so here once we get the hot resistance, let me take RA be the hot resistance of armature. Sorry, hot resistance of armature, and RSH, we don't take hot resistance of series shunt field. Okay, it is normal shunt field resistance. So either I will take the cold resistance and multiply it by factor 1.2, or I will run the motor at no load for elongated time and take the resistance immediately after the motor stops. With that, I will get what resistance are. Now in the second stage, we obtain the constant losses. How to obtain the constant losses? For that, we have to run the machine. Okay. So I will redraw the circuit diagram here, because now here I have to follow the procedure. RHA, and whenever you are drawing the DC motor or DC generator, please remember the language of drawing. It is not anywhere I can draw winding. Always the armature and field winding should come in parallel. Okay, that is the correct way of drawing. You can't draw winding here and armature here at the bottom, or winding at the bottom, armature at the top. Even in most of the textbooks, this mistake has been done. Okay, we are not simply showing some winding, some resistance, nothing. There is a meaning of representation, whatever we are doing. Okay. So here one more ammeter I will connect to measure the line current. So most probably from Monday onwards, you may not listen this background noise of my kids, because if the unlock happens, I think our college will start for we faculty, and we will take peacefully the classes in our college, in our faculty rooms. Here it is RA. Now this is the circuit connection. Okay. The armature current is, say, IA naught. Subscript 0 or O indicates the no load value. So here what I can say, let V be the applied voltage, I naught, no load line current, IA naught, no load armature current. Okay. Therefore, no load armature current is I naught is equals to, sorry, IA naught is equals to, I can take it as I naught minus ISH. Okay, ISH is shunt field current. You need not to mention. Already we have mentioned in the previous slide. Okay. Now, what is no load input to the motor? So what we are doing here is, we do the circuit connections, or before that, we see here, do connections as shown. Anyway, ensure motor is on no load. The motor is on no load only, but we have to ensure that. Ensure motor is on no load. Okay. Then start the motor. Then bring motor to rated speed. bring motor to rated speed by varying field rheostat RHF. Done. This is the experiment. Once this happens, note down the readings. Note the readings of all meters. We have missed one voltmeter here. Even in the previous circuit diagram. Done. This is the experiment. Very, very, very simple experiment. Okay. Fortunate is the one who will get this in external exam. And unfortunately, many people could not do this experiment also in many of the batches because of connections. Okay. So with this, I will get the readings. Now, how to interpret readings? Getting readings is one thing. Interpreting is the second thing. Okay. And the most easiest way to pass the electrical machines lab is to make the machine run. Done. If machine runs, then you can't fail. Why? Because machine will run properly only when the connections are correct. When connections are correct, half the battle is won in machine experiment. So it is very easy to pass in machines lab. Whatever the experimental values you get, that is the second stage of evaluation. Because evaluation is always conduction and calculation. If conduction is done, then you can't fail. But if you don't do the circuit connection only, you can't pass. Okay, that is very, very important. So now, once the process is followed, method is followed, I will get the readings. So what the readings tell us? Okay, so we have taken the readings of voltage, no load current I0, field current ISH, I0 can be calculated by using this expression. And remember, whether I want to find the efficiency of DC machine running as a generator or a motor, the Swinburne's test has to be always conducted taking the machine as motor, because I am giving electrical input to that. Even though this is a generator, I should make it run as a motor during my testing. Then I have to use the losses and expressions for generator to find out the efficiency of generator. Okay, that once we find the losses and efficiency expressions, then I will let you know. Okay, then when the machine is at no load, the input current drawn by the motor is I0, the input applied voltage is V. So what is the power now? V into I0. So no load power drawn by the motor is equals to V into I0. No load current multiplied by voltage. Voltage will remain constant whether load or no load, theoretically. Practically, it will drop slightly. Okay, then this is the no load power drawn or no load input. That is no load input to motor. Is equals to V into I0. Then no load input to armature is equals to V into IA0. See, this is not the power developed, it is V into IA0. Power developed by armature is EB into IA0. No load power developed. Okay, so don't get confused. This is V into IA0 is armature input. EB into IA0 is armature output. So armature output is mechanical, armature input is electrical. So V into IA0, or I can write this as V into I0 minus ISH. Okay. So any doubts so far? So since the motor is running at no load input, I have to consider. Any doubts?
No, sir.
Okay. Then today I will stop here because time is up. In the next class, we will see the further part of Swinburne's test. Okay, how to get the losses, what are the different losses, and how to lead in finding the efficiency. Okay.